Hey, Math 7195, Unit 9 continuing. We're into video 2. We're going to do a new test today. This test is called a goodness of fit test. In order to perform this test, we'll have to learn another new distribution. Last time we learned the F distribution, and now we're going to add on the chi-square distribution. And the goodness of fit test is a special case of a chi-squared test. So let's get right to it. Goodness of fit test is basically, you sort of already did something like this when we were trying to estimate the parameters of a Weibull distribution. Basically, you're comparing your sample results to what you'd expect to happen under some assumption. So if I have some data that I suspect is normally distributed, I can compare my observed data to data that I would get if it were normally distributed, and under that and then perform a hypothesis test. We can do that for the Poisson distribution or exponential or Weibull or any of those distributions. Basically, we're testing to see if our data fits a particular model. The test relies on a new test statistic called chi-squared. It's not really squared, it's just its symbol. Basically, it works like this, where you're taking your observed value minus your expected value. So basically, the numerator of this is the error. So you're taking your error divided by your expectation. So it's sort of like totaling up your relative error, because we're going to sum that up over the whole data set. So the calculation isn't, terrible to perform, but it definitely lends itself to using software. The conditions for this are, random data. We'll have frequency counts. Basically, you're making a histogram and you're comparing it to the histogram that you'd expect to happen under those same conditions. And the only thing we need to meet is that our expected frequencies are all at least 5. And even when they're not, there's a little trick we can do to make that happen anyway. This distribution relies on degrees of freedom. In this case, they're rather weird. It's k minus m, where k is the number of categories and m is the number of values obtained from the observed data needed to calculate the expected values. It sounds more complicated than it is, although it is a little bit complicated. This chi-squared distribution behaves somewhat like a t-distribution in that its shape depends on degrees of freedom. Your textbook uses this Greek letter N for degrees of freedom. It kind of looks like a V, but it's actually a Greek letter nu. It's an N. But we've been typically writing this as DF. The degrees of freedom change the shape of the distribution. And in fact, the degrees of freedom actually equal the mean. So whatever your degrees of freedom are, that's roughly where the mean of that distribution is. So here's the case where degrees of freedom are 20 and the mean is there, which makes it kind of convenient that you don't even have to do any calculation really to figure out where the mean is. And the variance is 2 times the degrees of freedom. We'll have a table for this for finding the area beneath the curve. You see that it's like the t-distribution in that its shape changes based on a single set of degrees of freedom, but it's different in that the thing isn't symmetric. So just because you know the area in the right tail doesn't mean you know the area necessarily in a corresponding left tail. You actually have to calculate the left separate from the right. But in Excel, we have functions that do that, chi-square inv and chi-square dist, and there are even right versions of them now. The table for the chi-square distribution, I said it reminds me of the t-distribution because the table is very similar in nature that way. You have degrees of freedom, down the vertical axis. You have probabilities across the top axis, and it's always given as area to the right. One thing you'll notice is that chi-square values are kind of weird compared to what we're used to looking at. We're used to looking at t-scores and z-scores, and they kind of vary from -3 to +3 roughly. Sometimes a little bigger with the t-distribution. But with the chi-square distribution, we get values sort of all over the place. It's not unusual to see a value of 100 or, in the teens. So it's a little bit harder to judge these chi-square values just by looking at them. We don't have the same number sense that we did for z's and t's, but we have the table and we can just interpret from there. Let's do a little example. This is kind of the classic one. When you buy a pack of M&Ms, it has 100 M&Ms in it. The company claims that 30% of all M&Ms are brown, 20% are yellow, 20% are red, 10% are orange, 10 are green, and 10 are blue. Well, do we believe them? We buy a bag of M&Ms and we count the brown ones, we count the yellow, red, orange, green, and blue, and we want to compare our observed results to what we expect to happen. Well, in order to get these expected values, our expectation is based off of a sample of size 100. So I'm going to build this little chart and then we'll go ahead and do the test. If 30% of these things are brown and I have 100 of them, then I expect 30, our frequency to be 30 there. Or if 20% are yellow, I expect 20, and 20% are red, and 10% are orange, and 10 are green, and 10 are blue. Are our numbers close enough to these expected values for us to conclude, yeah, we believe you, M&Ms, but that's the distribution of the colors? Or are our values different enough where we say, I don't think they're telling the truth. I think they're putting too many brown ones in there, for example. In order to do the chi-square test for goodness of fit, we need to calculate that test statistic. And the test statistic was, a summation. It was the sum of your O minus E squareds over E's. So I thought I'd just build a table. We can kind of do this one by hand because the numbers are easy enough. We need to do all these differences. So 33 minus 30, that's our first O minus E. And we have to do that for all of them. 6, 1. This one's -2, -3, -5. And then we can square all those. 9, 36, 1, 4, 9, 25. You see why we did the squaring there. It's kind of like we did with standard deviation back in the day, where in order to balance out this positive and negative issue, we'll just square everything, and that makes everything positive. Now we'll take these, basically our errors squared, and divide them by our expectation. So the first one is 9 out of 30. And then 36 20ths. And then 1/20, and 4/10, and 9/10, and 25/10. And in the formula here, we're summing all these up. Really, we have I equals 1 up to, how many colors did we have there? 6 colors, where we have OI, EI, and EI. So we need the sum of these guys, and that turns out to be 5.95. So we've basically calculated our test statistic. It's like step 5 of our hypothesis test. I just wanted to get it out of the way before we dove into this. There must be a claim somewhere. Oh, they are claiming that these are the breakdowns for each color. So that's our claim. Step 1 is that they claim the percentage of brown is 30%, and the percentage of yellow is 20%, and the percentage of red is 10%, and the percentage of orange is 10%, and the percentage of, I might have got the red wrong. I think red was 20%. Green was 10. And finally blue. That's why I put BR for brown. So I could go BL for blue. So that's their claim, that those are the percentages. If any one of them is far enough off, then it's not true, right? In order for it to be true, they all have to all be pretty darn close. If even one of them is a ways away, it could potentially mean we're off. Step 2 is set up our null and alternative hypothesis. Basically, they're saying that these are the percentages. They're all equals. So that's our null hypothesis. I'm not going to rewrite it. Our alternative hypothesis is at least one is different. Getting a little sloppy in my wording there, but you know what I mean. It will fail if at least one of these isn't true. Step 3 is pick alpha. I think it said let's use 0.05. Step 4 is check your assumptions. We need random data. And all expected values need to be greater than or equal to 5. Was that the case for our example? Our expected values are in this column, and yes, they are all greater than or equal to 5. If they weren't, we would need a larger sample size, right? If we only had 40 M&Ms to work with, and when we calculated these expected values, 10% of the blue ones, we'd only be expecting 4, and we wouldn't have enough data. So we would need to collect more. So we need to ensure that this is the case, and in this one we have enough. On to step 5. Step 5 we already did. It's calculate the test statistic. Our chi-squared value was 5.95. Step 6. We could do this either traditionally or p-value method. All goodness of fit tests are right-tailed. I mean, in this case, what would make these different? Some could be bigger, but if some were bigger, some would be smaller. It would have to balance out that way. Uh, so it would be hard to come up with a rule one way or another. So we just have committed to this as making them all right-tailed, which is sort of a function of the way this test statistic is calculated anyway. So we don't have to worry about the left tail. In order to, well, let's pick a method here. Maybe do traditional method. Looks like I have a whole blank page here. I could do this in. If I'm doing this the traditional way, I'll just draw some sort of, skewed curve. My axis is the chi-square axis, and I'm looking for a critical value where the area is alpha. So we're looking for chi-square subscript alpha. In order to get that, though, we need to know the degrees of freedom. Your degrees of freedom were k minus m, which is kind of confusing, I guess. The k isn't bad. It's k for category. Good spelling, I know. So how many categories did we have? We had brown, yellow, red, orange, green, and blue. So there were 6 different categories. That's k. The m is often just 1. We're used to n minus 1 as our degrees of freedom. And in this case, it will be 1. But let's explain why. Remember when we calculated these expected values, what did we need from our data in order to get these numbers? We needed the percentages, but that didn't come from the data. That came from the claim. In order to calculate these numbers, we needed to know one thing besides what they told us from the company. We needed to know this sample size. So there were 100 values. We took each of these percents times 100. So there was one thing that we needed to know from the data in order to calculate the expected frequencies. So that's what this M is. Sometimes the value will be 2 or 3. We'll do an example where you'll see when that pops up. So we have degrees of freedom of 5, and we have a probability of 0.05. We can go back to our chi-square table. Degrees of freedom are 5. Our probability was 0.05. So our test statistic is 11.070. Sorry, that isn't, I say that often, I think. The critical value is 11.070. The test statistic was 5.95. Which isn't to the right of the critical value. 5.95 falls somewhere in here. In fact, it falls pretty close to the middle. Remember, the degrees of freedom equal the mean for a chi-square distribution. So the mean of this distribution is, near the peak here. And then 5.95 would be relatively close to that. And 11 is quite a ways up here. So we're not in the rejection region. We'll fail to reject. Step 7. And then step 8 is your conclusion. The null hypothesis was the claim, and we failed to reject it. So basically, we're supporting the claim, but we have to do it in a weak way because we failed to reject. So we're going to say, we can't say they're wrong. There is insufficient sample evidence at alpha equals 0.05 to warrant rejection of the company's claim. That the colors are as stated. I'm too lazy to rewrite each of those percentages. You know, brown was 30% and yellow was 26 and red was 20. Basically, we can't say they're wrong. That's what this says, which essentially says they're right, but it does so in a weak way. If you don't like the chi-square table, of course, we could have gotten this value using the function in Excel. There's chi square. It's not chi dot square. It's chi sq. And we want a value, so this will be inv dot right. And then we put in our 0.05 and our degrees of freedom. And that'll get you this 11.070. You could use chi-square dot inv without the right and then put in 95% and 5. I think then you have to put the cumulative in too. If you're a p-value sort of person, we would take our chi-square distribution, we'd place 5.95 roughly in the middle, because 5 is roughly the middle for this one, and we find the area to the right of it. So the p-value, we can't get it exactly from the table. At best we could do is get a range. If we go to our table, remember we'd be in row 5, we'd be looking for the number 5.95, and it's not in there, but it's somewhere between these two. So our p-value is somewhere between 90% and 10%. It's a pretty wide range. But it's still bigger than 5%, so we would still be able to come up with a conclusion based off of that terrible range. If we're using Excel, we can do much better, obviously. We can get the p-value. That's just going to be a chi-square dist. And we might as well go to the right of 5.95 with 5 degrees of freedom. From Excel, you get 0.3111. So a big p-value, which is much bigger than alpha, so you fail to reject the null hypothesis. I did do this in Excel as well, but I thought I would do the next, we'll do one more example. We'll just do the whole thing in Excel, just to make sure you can handle this one. This is a type of test that you pretty much want to use Excel on. The example we just did, the numbers are nice. They're nice integers. We didn't have to do any weird rounding or anything. Everything was easy to add together. But as soon as you have decimal values, uh, it gets a lot more complicated, and you'd probably want to use Excel. That's what we'll do with this next one. We'll do a little Excel demonstration. Uh, we have trucks arriving at our warehouse. Sometimes during a given hour, no trucks show up. Sometimes during a given hour, one truck shows up. Sometimes 8 trucks. I guess sometimes 97 trucks could show up, but that's very, very unlikely. We keep track of it over a period of time on randomly chosen hours, and 52 times we saw that no trucks arrived during an hour, and 102 times we saw 3 trucks arrive during an hour, and twice we saw 8 trucks pull up to the warehouse. And we never saw 9, 10, 11, etc. We say that in these queuing problems, a Poisson distribution often fits when we're talking about arrivals into a queue. So let's see if the data that we're observing does fit a Poisson distribution. But in order to do that, we would need to know the parameter lambda. So we're going to first maybe estimate that based off of our data. And then we'll conduct a test and see if this data fits a Poisson distribution with the lambda that we sort of discover based off of this data. So I'm going to jump to an Excel sheet here. I've already copied and pasted the question. I copied and pasted the data, and I added up how many hours we kept track of. We did this experiment 500 times. So on 500 different hours, we kept track of how many trucks arrived at the warehouse. In order to find the average, we could just take the average of 0 to 8 and go, well, I guess it's 4. But that wouldn't be correct because you can see it's weighted. We're most likely to have 1 or 2 trucks, and we're very unlikely to have 7 or 8. So we can't just say the average number of trucks arriving is 4. Remember when we did expected value, the expected value for number of trucks arriving? Let's see, can I write on here? Pens. Sure. Remember expected value for a discrete distribution was the sum of the outcome times the probability of that outcome? So what we could do is actually calculate this. So I sort of built a table here to try to calculate this average. And let's see here. What we could do is, P is a percentage. So let's calculate the relative frequencies. Right now we have the raw observed values, but we could say this first value it was 52 out of 500. So C9 divided by $C $18. So I'm going to calculate the percentage of time that we saw no trucks during a given hour, and it's 10%. And because I set up that formula nicely, I can just copy it down, and I can get all the percentages. So 1% of the time, 6 trucks arrived. And 0.4% of the time, 8 trucks arrived. I added them all up just to make sure everything's still working. It's equaling 100%. Now to calculate the expected value, I take the outcome times its probability. So 0 trucks times 10%. That's X times P. So B9 times D9. And I do that for all of them. When I add all these together, that's my mean. That's the expected value. I probably should have been clearer here and put brackets. It's the sum of the x's times p's. So our lambda ends up just being this value in cell E18. In the instructions there, I believe it said round it to 1 decimal place. So let's do that. Right now it's given as 2. Excel's keeping an infinite number actually. So I'm going to say L. I'm going to change the font so that I get a lambda symbol. So I have lambda, and then I'm just going to round that. Round cell E18 to 1 decimal place. And now it's 2.0. So now we have our lambda. You're like, where is he going with all this? Well, I need lambda in order to then do my Poisson probabilities. What's the probability of having 0 trucks arrive if on average 2 trucks arrive? What's the probability that 2 trucks arrive if on average 2 trucks arrive? What's the probability that 8 trucks arrive if on average 2 trucks arrive? That's a good old Poisson question. So Poisson dist. Our x value is in cell B9. Our mean is now what we just calculated for lambda there. So we have that it's in cell D20. Now, E20. Notice I put dollar signs around that one because I'm going to copy the formula down, but I want it to always look at the same lambda the whole time. And in this case, we're so used to always putting cumulative, but in this case, I don't want it to be cumulative. You'll see why. The probability of having no trucks arrive if on average 2 trucks arrive is 13%. We observed 10%. So basically we're comparing these values. And we're going to do that for then all of the rest. You can see why you'd want to use Excel for this. You have to do a lot of probability calculation. Now, these don't all add up to 100%. We're off by a little bit. And the reason for that is we've only considered 0 to 8 trucks. But there could be 9 trucks or 10 trucks or 400 trucks. They'll all have really small probabilities, but that's where the missing probability is. But to 3 decimal places, we're there. These are expected probabilities. Now I want to convert these probabilities into frequencies, right? If 13% of the time I see 0 trucks, well, how many, I guess I need to multiply this value by the 500 in order to get that frequency. 13% of 500. So I'll say F9 times 5. I could just hard code 500 in here, but I'll say it's in C18. That way my spreadsheet will be maybe more versatile for other things. So we observed 52 trucks, but we expect 67.67 trucks. Actually, that's not trucks, that's times. 52 times we saw 0 trucks. We expect that 67 of our 500 hours would have no trucks arriving. Do that for all the rest. This should add up to close to 500. It's off again by a little bit because of these probabilities didn't quite add up either. We observed sometimes 5 trucks arrived in an hour. We saw it happen 12 out of 500 times. We expect it to happen 18 out of 500 times. So we're comparing our observed unexpected. We built this whole table basically so that we could look at this column and this column. In our M&M example, we basically were able to jump to the expected value very fast because they gave us the percentages. Now we can build the rest of this thing. We can calculate our chi-square, figure out our errors here. It's observed, which is in C9, and then subtract our expected, which is in G9. And I need to make my column a little wider. Do that for all of them. And then I need to square those guys. So we'll say equals H9 squared, and then divide that by our expected value, which is in G9. It's this thing squared divided by this one. Make my column a little wider so it fits. Calculate them all, and then here's the total. This is maybe my chi-square value. Sadly, we've made a little bit of a mistake, but I wanted to make this mistake so that you won't make this mistake. Remember when we're doing a chi-squared test for goodness of fit, we had basically 2 conditions. We had random data, we picked 500 different times to collect these values. We've met the random part. Now, we also need the expected values to all be greater than or equal to 5. Well, we were doing pretty well here. Most of these are greater than or equal to 5, except the last 2. The probabilities got so low that we aren't representing these categories very well. They're under 5. So what we could do to fix this is basically combine 3 categories into one. Have a category called 6 or more. And that way we'll have enough data. If we combine this row here with the rows beneath it, then we'll have expected values of greater than or equal to 5. It's a little bit sneaky, right? So what I'll do here is maybe I'll delete these guys. And basically I'm making a combination of these 3 rows. So for my observed minus expected, it will be the sum of, C15 to C17. And then we'll subtract the sum of G15 to G17. So we'll have our observed minus expected there is for the last 3 categories. So we've actually changed it. We don't have 9 categories anymore because we've now combined 3 into 1. This last spot needs to be fixed too because the denominator should be that sum of expecteds. So what will it be? G15 to G17. I must have been missing a bracket. Yeah, it was. I needed one more bracket on the end. It put it in for me. So now this is my chi-square value based on 7 categories instead of 9. We can, quickly run through the test. Step 1. They're claiming it's Poisson with a mean of 2 trucks per hour. I'm doing this really rough now. Step 2, HO. Poisson dist with mean of 2. It isn't. That's getting really rough. Step 3 is pick a alpha. How about we go 0.05? Step 4, check assumptions. Random data, all EI greater than or equal to 5. We've met that condition. We didn't, but we faked it until we got it. Step 5, calculate the test statistic. Chi-square it's an I-18. We get a test statistic of 9.217. Step 6. Shall we do the p-value method? They're always right-tailed. Maybe say that. All goodness of fit tests are right-tailed. P-value is the area to the right of 9.217. So we'll say chi-square dot dis dot right of 9.217, which is E28. And then we need our degrees of freedom. Oh, geez. Maybe we should have paused and done that first. Yeah, I don't know what it is. I'm going to guess it's 4. Before we calculate the p-value, we need to figure out these darn degrees of freedom. Degrees of freedom equal k minus m. In this case, we had 9 categories, but we eliminated 2 of them. So we were down to 7 categories. And then m is what you needed to get done in order to calculate the expected values. To get these expected values, what did we need from the data? Obviously, we always need the 500. So it's always at least 1. But we also needed to figure out what lambda was. So basically, we calculated lambda in order to calculate these probabilities in order to get these expected values. So we needed to know 2 things. From the data, we got n and lambda. So that's why our m for this one is actually 2. So it's 7 categories minus 2 things. I know that's confusing. When in doubt, put a 1 if you're not sure. It's not usually much more than a couple. Now we can calculate our p-value. I was wrong. It wasn't 4. It was 5. The p-value is kind of big. Step 7. P-value is greater than alpha. So we fail to reject the null hypothesis. What does that mean? In this case, the null hypothesis was the claim. They were claiming it is a Poisson distribution. So we're not rejecting that. There is insufficient sample evidence at alpha equals 0.05 to reject the claim that the data follows a Poisson distribution with lambda equal to 2. It's a bit much to do one of these. I often put one of these on the final. So uh, if we did a Poisson right now, I mean, take a guess what's on the final. Oh, I wouldn't be surprised if there was something about a binomial where you had to do this column using the binom dist instead of Poisson dist. Or maybe I'll say a Weibull. And I'll tell you what alpha and beta are for the Weibull distribution, and then you'll calculate these probabilities. Or a normal or an exponential. You can see it's easy to come up with, other examples. So be able to do this. I typed up a nice version here where I wasn't quite as crude in my, my steps there. And I was a little more careful explaining things. So if you want to have a better template, there's one in the document here called Truck Solution. So that's a goodness of fit test. We've done a lot of different tests now. Part of the problem you're going to start running into is figuring out what kind of question you have. They're pretty easy when they're in the lecture notes because we just learned the topic and then we do an example. But eventually they start, we're going to mix them all up. And yeah, that makes it a little trickier. But I'm confident we'll figure it out. I think that's it for the goodness of fit test. And that's it for this video. So I guess I will see you all in the next one. Have a good one.